Can you see the presentation?
Yes. Yes.
That's good.
Yeah. Okay, I think we can probably stop now. Since people are still joining, I think they will join later during your talk. So I'll just start with an introduction first. Hello, everyone. Welcome to our EA seminar today. So today we are excited to invite Dr. JC Stinville as our speaker. So JC holds a PhD in solid mechanics, materials science, and mechanical engineering. He joined the research group of Teresa Pollock at the University of California, Santa Barbara, focusing on experimental development of in situ mechanical characterization techniques. Last year, he is appointed as the assistant professor in the materials science and engineering department at the University of Illinois, Urbana-Champaign. His research interests include mechanical and environmental performance of metallic materials for high temperature, energy, and environmental applications. Now I'll hand over the mic to JC. Let's welcome JC. And JC, if you are ready, please go ahead.
All right, thank you very much for this introduction. So today I'm going to talk about the fatigue strengths of polycrystalline alloy. And I'm going to detail the localization of the plasticity in this kind of alloy and try to relate this to fatigue strengths. So before I start, I want to acknowledge my co-author in the different university. So it's work I have done. I started when I was a researcher at the UCSB, and I continue this work when I arrive here at the University of Illinois. So I want to acknowledge all my co-author at UIUC, UCSB, but also at the Institut P Prime in France. I also want to acknowledge my research funding, so Department of Energy and General Electric. So yeah, as I mentioned, I will detail fatigue strengths of metallic alloys. So today I'm going to restrict myself on metals that do not display any metallurgic defect. So all the data I will present are only related to crystallographic initiation, for instance, in fatigue. So on this slide, I'm presenting the fatigue strengths on the left as a function of the yield strengths or ultimate tensile strengths of metallic alloys. So it's data from the literature, and all the test has been done in the very high cycle fatigue regime. And as you can see, you have this relationship between fatigue strengths and let's say yield strengths or ultimate tensile strengths. And for materials that display very high yield strengths, fatigue strengths increase. There is another way to present this kind of data, and is what I am doing in the middle plot here, where I present the fatigue strengths as a function of the yield strengths and ultimate tensile strengths again. But here the fatigue strength is represented as a percentage of the yield strengths or UTS. So it's kind of a way to represent, it's what we call the fatigue ratio, and it's a way to represent the efficiency of a material in a fatigue. And as you can see, plotting the data in this way, you can notice that materials that have a very high yield strength, so the structural material, for instance, they tend to have their fatigue strength below, let's say, 40% of their yield strength, for instance. So for this material, you have a very low fatigue efficiency. And it's for this reason, fatigue strength is a very important property for structural materials. I want to show you two examples here using Inconel 718 nickel-based superalloy. So this kind of material are used for high temperature application, but here I am only detailing room temperature fatigue properties. So you can see the microstructure of this alloy on the left, where you see the different crystallographic grain. This kind of alloy display a lot of twins. And we process this alloy in two different ways. The conventional way, where you do edging treatment in order to develop precipitate at a very small scale. And this gives a very high strengthening for this kind of alloy. And you obtain the red curve. So you have the stress strain curve here in the middle, where you have your yield strength, which is for this kind of alloy close to 1100 MPa. You can also process this alloy to obtain a solid solution. So you do a water quench after forming the grains. And in this case, you prevent the occurrence of precipitation. And you only have a solid solution strengthening, and you obtain the blue curve. So you have the same grain structure, but you do not develop precipitate. And as a consequence, your yield strength of this alloy is pretty low, around 300 MPa. And so we tested both of these alloy in fatigue. And first, we noticed that you have the same kind of initiation. So in this regime, for the fatigue strength, you initiate internally, and you have a crystallographic facet, which is actually near twin boundaries. And the idea was to keep the same grain structure, but in the same time to obtain different yield strengths for this material. And I just want to display the fatigue results now. And it's what I do here on this plot. So you have the maximum stresses as a function of the fatigue life. So we tested quite a few specimens in the very high cycle fatigue regime. And the dashed line display your fatigue strength. And you can notice that despite this huge difference in yield strength, you have almost the same fatigue strength. Basically, the performance of this alloy in fatigue, or at least the fatigue strength, is very similar for the one with precipitate and the one without precipitate. And so it's quite surprising to observe this kind of results. And now if I display these results as a function of this plot I presented earlier. So you have the fatigue strength as a function of the yield strength, let's say. And I display with these two crosses in blue the solid solution. So you have a low yield strength, but a very high efficiency in fatigue. So we are almost close to 100% of the yield strength, the fatigue strength. And in red is the one with precipitate, where you develop a high yield, so you have good monotonic properties. However, the fatigue strength is around 30% of the yield strength, so it's very low. So you have quite bad cyclic properties. And so what I am trying to understand, and is that the purpose of this study, is to understand the link between this monotonic property, so the yield strength, for instance, and the fatigue strength. And if you can understand this link, you may be able to design a material that display high yield strength, but in the same time, very efficient in fatigue. So we know quite a lot on fatigue of metals. And we know that the fatigue strength is really controlled, or the fatigue life in the regime where you determine the fatigue strength is really controlled by the initiation of the damage. And this initiation of the damage is really related to localization of plasticity. And so it's easy to think that we may have a link between monotonic property and fatigue property if we investigate the localization of the plasticity. And I just want to show you an example here from the literature. So for instance, if you consider copper, you have the fatigue strength, which is above the yield strength. And we know that in this material, you have specific structure, fatigue structure, persistently bent. and they extend the location of the plasticity, extend on a quite large region, so at the micron scale. For instance, you can see a feature that extends about, up to 5 micrometer at the surface of the specimen. However, if you consider high yield strength materials such as the nickel-based superalloy, in this case, you localize the plasticity in a very, very small region, so at the nanometer scale, and you have a lot of extrusion during cycling. So you can start to see you have this relation. If you have high yield strength material, you develop very localized plasticity. And if you have low yield strength material, you will homogenize the plasticity, or you will develop fatigue structures that are quite large. So now the aim is really to understand if we can measure this kind of the localization of the plasticity and relate this to fatigue strength. And that's the aim of this study. So to do that, I use different technique, but I will only detail one of them, which is the one in the middle, high resolution digital image correlation, which allow you to capture quite rapidly the localization of the plasticity during loading. In order to capture the fatigue strength, we also use an accelerated testing, which is a very high cycle fatigue testing. And you can test the specimen at 20 kilohertz. So you can apply 20,000 cycles per second. And it helps you to determine the fatigue strength rapidly. All right, let's come back to the high resolution digital image correlation. So this technique is used in situ. So I do that inside a scanning electron microscope in order to have high resolution measurements. So as you can guess, when you deform metals, you develop structure that are at the nanometer scale. So you really need to have this very high resolution to capture these structures. You can couple this measurement with in situ testing, or even ex situ testing if you want to do more complex testing such as fatigue loading. What you obtain at the end, so you obtain the strain field at the surface of the specimen during deformation. And you can relate this to the microstructure if you use, for instance, EBSD measurement. All right, the IC is quite simple. So you apply a speaker at the surface of the specimen, and you track the displacement of the speaker during deformation. And from the displacement field, you can obtain the strain field. You need to have high resolution in order to capture the feature, the physical feature during deformation of metals, which here in this case, in this presentation, is all related to slip. For instance, on the left, if you use a large subset, if you interrogate a large region during DIC measurement, you actually tend to average your results, and you are not able to resolve all the slip events during deformation. And on the right, if you start to have a very low high resolution, you start to resolve all the slip events. And we really want to capture that in order to quantify the localization of the plasticity in metal during cycling. There is another fact is that when you deform a metal, and if you compare the initial image to the deformed image, and when you have slip, the displacement obtained is a discontinuity. So the slip produces a discontinuity if you compare initial to deformed image in DIC, and conventional DIC code cannot handle discontinuity inside the inside the displacement field. And this discontinuity, of course, is coming from the emergence of the dislocation at the surface of the specimen during deformation. So we did develop a code to capture this discontinuity. And one of the advantages using this advanced code is that you can quantify the displacement induced by slip. So this code is what we call the EV side DIC. It's actually quite simple in a sense where you just during DIC, so you divide your subset. So the subset is at a very small scale, and you divide this subset in multiple parts. And by doing that, you can take into account discontinuity during DIC calculation. I don't want to detail this too much, but using this code, you can identify if you have a discontinuity inside the subset, the location of the discontinuity, and the amplitude of the discontinuity. And so what you have physically at the end, let's say on the right, you have a schematic of the formation of the slip band during the formation of metals. And the DIC code gives you this green vector, which is basically the amplitude and the direction of the displacement induced by slip during deformation. And you really have a quantitative measurement of here the localization per slip, so slip localization. If you compare the result to conventional DIC code, you also have a quite large increase in resolution. So for instance, I am displaying the displacement in the plane, but I use a 3D representation. So on the left from conventional DIC and on the right from the EV side DIC. With conventional DIC, of course, when you have a discontinuity in the displacement, you obtain a gradient. And it's very difficult to quantify the amplitude of the discontinuity. With the EV side, you really start to capture the amplitude of the discontinuity, and you also have a larger resolution that allow you to really capture the displacement near the discontinuity. Okay, so what you obtain at the end using this code. So you use DIC, you can do this in situ, so you can apply a monotonic deformation, for instance, or cyclic deformation. You can capture the microstructure, so you can obtain the grain structure. And in the same time, you have the strain field. So it's what I represent on the left. The spatial resolution is enough to capture all the slip events. So all these bright bands are related to a slip that occurred during deformation. Using the EV side in the middle, in the same time, you can also capture quantitatively the amplitude of the displacement. So for instance, you can see this band in the middle here near the twin boundary have an amplitude quite high compared to the other slip events. And here is giving in nanometers. So the displacement induced by slip, for instance, is close to 130 nanometers. And And on the right, I'm just displaying the displacement in the plane, but this in 3 dimensions is just a fancy way to represent all the step induced observed with the EV side DIC. Okay, so we have this. So all the data I presented up to now were related to monotonic deformation. But you can also apply this during cyclic deformation, and it's what I do here. So I just apply one cycle. So I loaded the specimen in tension, so you can see the black curve, and then I unloaded the specimen to 0 stress, and I did the high resolution DIC measurement. And you obtain the map on the left, where you see all the slip events and as a function of the microstructure on the bottom. Then I loaded the same specimen, but in compression, to come back to about 0% plastic deformation. And then I did the high resolution DIC measurement for the exact same region, and you obtain this kind of map. And what you can see is that most of the slip localization or the slip events reverse during the compressive phase. You basically close your extrusion during the compressive phase. However, in specific region, and here in the middle, you still see some slip events, and that's a direct measurement of your irreversibility, meaning that this slip event didn't recover during compressive load. And this is very important because we know that this kind of region where you have very high irreversibility are the regions that trigger damage. So here we really have a quantitative measurement of the slip irreversibility during cyclic loading. We can even go further using this advanced code, and it's just, I want to detail this very briefly here. So I'm focusing on a specific region where we have very high irreversibility. So on the top, it's after the tensile part of the first cycle, so you can see all the slip events. The amplitude is given in nanometers. And on the top right or middle, it's after at the end of the first cycle, so after compression, tension compression. And you can, as I mentioned, you can see that you still have some amplitude for the slip event. And what I displayed at the bottom is the direction of the shearing for this slip event. And when it's green, is basically you have a positive value, so it's giving in degree here, but you have this white, the direction is indicated by these white arrows. And it's positive, so you have extrusion. And of course, you did the test in tension, so you develop extrusion. However, after the compressive part, you notice that some of the bands, they are still in extrusion, but now some of the bands also are in intrusion. And so with this kind of technique, you can also capture this extrusion-intrusion during cycling. And this one is also related to your irreversibility and also can explain, you can directly relate this to damage. So you really have a measurement of your irreversibility and you have a measurement of the localization of the plasticity, quantitative measurement, during deformation, during cyclic deformation. And you can do that for a statistical, or you can do this in a statistical way where you can investigate large field of view and you can display, for instance, during this cycling after tension and compression, for thousands and thousands of slip events, you can display, for instance, their maximum intensity after tension and after compression. And you obtain this kind of plot in the middle where you notice that after the first cycle, you still have some extrusion, so it's a red. You still have some extrusion, slip bands display some extrusion, and some other slip bands display intrusion. And you can calculate the difference, for instance, and relate this to your localization of plasticity. Okay, so let's come back to this two model material and to try if we can use this tool to understand why the solid solution, for instance, is way more efficient in fatigue compared to the precipitate. So I did the measurements during monotonic loading to start, and is what I display here. So I apply a plastic deformation, so 1.2% plastic deformation, and I did the high resolution DIC. So you obtain this kind of map. You can see the strain field, you can see the microstructure on the left. And at the bottom, I just display the amplitude of the localization for a small region of interest. What you can see is that most of the bands, they display value of localizations that can reach up to, let's say, 150 nanometers at this applied plastic deformation. So I did the same for the solid solution, so the alloy with the lower yield strengths. And you obtain these results. So I apply the exact same plastic deformation. So same plasticity macroscopically. However, at the scale of the grain, you develop way more slip bands. So and in the same time, the amplitude of the slip event are never higher than 60 nanometers. So in this alloy, you apply the same plastic deformation, but you homogenize your plasticity. You develop more slip bands and the intensity of these slip bands are lower compared to the precipitate. And of course, you can do this a quantitative measurement, and it's what I display on the left. So I extract all the slip events. So in this kind of data, you have thousands and thousands of slip events. you can extract the intensity of this slip event. You can also normalize by the length of the slip event in order to take into account the grain size. And I display this for the two materials as a function of the applied macroscopic plastic strain. And again, for the material in red with the precipitate, the localization of the plasticity is very high. And when I say parallel slip, it means that the highest localization always occur near twin boundaries when you have a slip band parallel to the twin boundaries. So that's a specificity for nickel-based superalloy. And for the alloy in the solid solution with low yields, you can see the localization is very low compared to the other one. And this may explain why you have very higher efficiency in fatigue for the alloy without precipitate, because it developed very low localization, and so the plastic location is lower and the damage occurs later during fatigue. However, it's only 2 points, and it may not be representative of all metallic materials. So what I did next, I went to the lab and took all the metal I had, only metals that deformed by slip and at room temperature, and materials that do not display a lot of defects, such as inclusion and etc. And I took HCP, BCC, and FCC material, and I tested the material during deformation in monotonic loading, and also during cyclic loading. So when I say cyclic loading, I only did one cycle where I did measurement after the tensile part and the compressive part to come back to, so I went to the yield of the material and I came back to a 0% deformation after the compressive part. So to not have any macroscopic residual plastic strain. Of course, at the scale of the grain, you still have some irreversibility, so you can capture that. And I did measure that using the heaviside DIC. So you can see some example on the left. It's always hard to display the full map because the map are too large, and so you cannot really appreciate the resolution. So here I just display a very small region of all of the map, or a few of the maps. So what I'm doing, let's say for one example here, or a few examples here. So I capture about between 1 millimeter square to 2 millimeter square to be representative of the microstructure. So by doing that, you capture large field of view and you capture a lot of crystallographic grain. And so you are representative of your texture, of your materials, of your microstructure. Then you do high resolution digital image correlation and you can obtain all the slip bands. You extract all of these slip bands. So we use different techniques. You can use conventional segmentation technique or machine learning technique when the bands are not totally straight. Sometimes it's difficult to do with conventional technique. Anyway, you can extract this. You don't want to do this by hand because you have like thousands and thousands of bands. But you use advanced tool, segmentation tool to detect that. You obtain the profile along the slip bands for all of the slip bands. So I give just example for different materials. And you can extract the maximum intensity. And you do that for thousands of slip bands, and you can calculate the average, for instance, and you display this as a function of the microscopic plastic strain. It's what I do at the bottom. And you can see some material develop low slip band with low intensity, and some other material develop slip band with a very high intensity. So here is during monotonic loading, and I display the results only at the yield strength of the materials. So I have the yield strength, let's say the plot on the left. I have the least strength as a function, or I have the maximum intensity for all of the slip band as a function of the yield strength. For all kind of material, all the material I tested, the point displays the average value for all of these slip bands, and the bar displays the maximum the 5% highest value. And of course, in fatigue, we are more interested by the highest value because that's the ones that develop damage during cycling. What you can see is that for FCC and FCP material, with increasing yield strengths, the material with high yield strengths, they tend to develop very high localization compared to material with low yield strengths. That's the case for the average, but that's also the case for the highest value. For BCC, it's a little bit more complicated. They tend to develop lower localization in average because, of course, you have more slip system possibly activated and you have cross slip at room temperature. You can also, with this statistical analysis, extract the spacing of the slip traces between the slip traces. And you, of course, obtain the same trend in a sense where material with high yield tend to develop high spacing. So you develop less slip bends, but these slip bends, they display very high intensity. Okay. And then you can also do the measurements as mentioned during the first cycle, so after tension and compression, and compare the result to the fatigue strength. And it's what I display here. So when I do testing at ratio of -1, I use tension compression. So I just display the amplitude of the localization after the first cycle after compression, so at the end of the cycle. And when I compare with test at ratio of 0, when you have only the tensile part during cycling, I of course compare only to the tensile part, so the first cycle. So you have the fatigue strength obtained by very high cycle fatigue testing. Here is displayed as the percentage of the yield strength. And on the x-axis, you have the slip localization amplitude in nanometers for the 5% highest value. So on the large map after the first cycle. And what you can see is that the fatigue strength as a percent of the yield is directly related to the localization you will produce during the first cycle. So when you have a ratio of 0, you don't reverse, but when you have a ratio of -1, you do reverse and you recover some of the slip event, but some other you don't recover. And so you have irreversibility. In this measurement, after the first cycle, you can also capture this irreversibility. So here we do have a relation for most of the metals here between fatigue strength and the amplitude of the localization during the first cycle. So the first cycle can inform on your fatigue strength. So it's a very interesting result here. And in the same time, if you want to capture the fatigue strength, it's very complicated and very expensive. And it takes a very long time because you need to test multiple specimens. However, if you want to capture the localization of the plasticity during the first cycle, so it requires only one cycle, and it requires these very high resolution measurements that are quite fast, I would say. You can do this in one day. So you have a way to evaluate your fatigue strength now by using this kind of measurements. And that's what I'm trying to do right now is that can we use that to produce, for instance, materials that are efficient in fatigue. So you want high yield strength material, of course, but you want the materials that also display a fatigue strength close to their yield strength. And this kind of tool can be used, and I want to demonstrate this for this purpose. First, you can use that to understand why certain materials have better fatigue strength than others, of course. And I just want to show you one specific example, which has been investigated in the literature, and we didn't know why this specific microstructure display higher fatigue strength. So you have a microstructure, we call this necklace. So you have, it's a nickel-based superalloy. You have large grains. These grains are not fully recrystallized, so you have lattice rotation. The twin boundaries are not coherent anymore. And between this grain, or around this grain, you have small grains that are fully recrystallized. And it's for this we call this necklace. And this kind of alloy display a slightly higher fatigue strength compared to the fully recrystallized with the same average grain size. And it was not obvious. Why? Because when you have large grain in fatigue, they tend to a microstructure with large grain tend to have a lower fatigue strength because the amplitude of the localization is always higher and etc. So it's scaled with grain size. And so by doing high resolution DIC, we were able to understand why. So here is just an example. So in this kind of superalloy, you develop high intensity of localization near twin boundaries, and that initiate crack quite early during cycling. However, when you have this large grain and fully or not fully recrystallized, the twin boundary, they are not coherent anymore. So it's not a 1-1-1 plane. And the slip planes, they want to develop near this twin boundary because you have high stresses. However, as you can see, the slip doesn't develop across the entire twin boundaries. And you break the localization in multiple slip bands. And these slip bands have lower intensity compared to the material where you are fully recrystallized with coherent twin boundaries. And so you really, by breaking the coherency of the twin boundary, you really decrease the localization of the plasticity near the twin boundary. There is another effect. In this large grain, you have lattice rotation and you have immobile dislocation. So you have a large density of GND and SSD. And as a consequence, when you develop slip inside this grain, if you use high resolution DIC, but only the strain map, it seems like there is only one slip band. But when you look close, for instance, in one for the slip band 1 and 2, you notice that you have multiple slip bands actually. Here you can see. And these slip bands, they have lower intensity compared to if you had only one slip band. So basically, if you decrease this in this large grain, the amplitude of the localization, the slip intensity is lower, it's more homogeneous. And as a consequence, you have higher fatigue strengths. And if you do the statistical analysis, when you extract the intensity, it fits very well with the relationship we observe between fatigue strengths and the localization after the first cycle. So you see this kind of tool can be used to that, but you can also design, and is what we did on a nickel-based superalloy. You can design new alloy to improve the fatigue properties. So here is a Roney 65. With this kind of alloy, you have a way to control the location of precipitates, so gamma prime precipitates, so this large precipitate. And you can process the alloy to break the coherency of the twin, for instance, the twin boundary, but also to develop the twin boundary near this precipitate. And so basically, for instance, here you can see a precipitate in the middle of the twin, and as a consequence, when you deform this alloy, the localization of the plasticity is reduced, and you see you don't have any localization or slip that cross the precipitate. And so you reduce the localization near twin boundary, and as a consequence, you can improve the fatigue properties. And so you can start to design a new alloy with improved fatigue property using this kind of approach, and you do improve slightly the fatigue strength. However, we are still very far from a material that is efficient in fatigue with a very high yield. This really related to the intrinsic localization in FCC and HEP. You will always develop a relatively high localization of plasticity. So you will always have relatively low fatigue strength. However, when you come back to the data, here where I display the yield strength as a function of the maximum intensity, you can notice that maybe if we use a BCC alloy, we may be able to develop an alloy where you are with high yield, but also in a efficient in fatigue. Because BCC at room temperature tend to homogenize the plasticity. And we know that from the literature. For instance, if you display the fatigue strength as a percentage of the yield, as a function of the yield strength for BCC, FCC, and HCP, the BCC, they'll always display a better fatigue properties. However, for instance, if I display this BCC, so it's a high entropy alloy. So it's this new kind of alloy where you mix different elements in the same equiatomic percent. And this alloy, when you do fatigue strength, so you develop also, you have the same fatigue strength than FCC or HCP. And this is related because if you investigate the localization of the plasticity, the highest value in average, most of the values, they are pretty low, but the highest value, they are still very similar to the one observed in FCC and HCP. And as a consequence, the fatigue strength is also very similar. So if we did investigate this alloy, and we noticed that the highest value only occur in specific orientation, a specific crystallographic orientation. And I display this here. So in this inverse pole figure along the loading direction, I display different grains, so a lot of grains. So it's a statistical analysis. And the color displays the intensity of the slip, the maximum intensity of the slip for all of the slip bands that develop inside the grain during cycling. And you can see only a few grains develop very high intensity. And that's the grain on the top here, for instance, you can see very high intense slip band. And on the grain on the bottom, you tend to develop a lot of slip band with a very low intensity. And so the idea I am working right now is that can we process this alloy to prevent the occurrence of this crystallographic orientation and to prevent the occurrence of this very high localization. And it's quite complex because in BCC you have activation of different slip system. You can even activate a non-crystallographic plane. You have a high frequency of cross slip. You activate a lot of cross slip. But if we succeed to develop this kind of alloy, for instance, and we can prevent the high localization in this specific grain, we may be able to have an alloy with you have high yield strength and at the same time very high fatigue efficiency. And with this, I will just conclude, and I will thank you for your attention.
Right. Thank you very much, JC. That's very interesting talk. Has anyone get any questions for JC? You can just raise your hand, ask it directly, and then probably put your question in the chat. Oh, go ahead, Elan. Yeah, go first. Oh, you're muted, Elan.
Oh, hi. Can you hear me now?
Yes.
Yeah. Yes.
Yeah. This is thanks a lot for your very informative talk. It's very interesting and full of information indeed. I'm quite sure there are many questions incurred. Just got one from my side. So basically, in one slide, sorry, I forgot the slide number, but you slide in the text. So basically, you expect lattice rotation developed in large grains, and which would help the fatigue performance, right? I think.
Is that fine?
Yeah, I think I'm just curious what's the mechanism there? So basically, the correlation between large lattice rotation and the enhance of the high fatigue performance.
Yeah, so it's a very good question. So basically, in this alloy, you see this large grain.
Yeah.
You have a lot of lattice rotation. You also have SSD. You have a high density of immobile dislocation.
Yeah.
And so when you develop a slip in this large grain, the slip tend to stop in the middle of the grain.
Oh,
the slip tend to stop in the middle of the grain. And it is not, of course, if you are fully recrystallized because of avalanches and etc., you never stop. The slip never stop the dislocation. They just go. Here they stop. So we are still investigating that. We believe it's related to maybe because you have this lattice rotation, it can be a reduce in resolve shear stress. because you have, and then the dislocation doesn't have enough energy to continue to move. It can be also, you have immobile dislocation. So you, for instance, here you can see on this example, the slip stop, and you develop a new slip bend near it. So you may have, because you have immobile dislocation, you may activate cross slip maybe in this specific location. It's difficult to say. It's a very good question, and we are still investigating that. We believe it's related to the change in resolve shear stress, and that, but we will need calculation to really evaluate that.
All right, thanks. And just a very quick follow-up. So do you believe that this phenomenon is general, is it generic for all of the similar twin containing alloys, or it just works for the material you have presented?
Yeah. So you mean the lattice rotation here? Yeah. So we are really starting to investigate that. What I can tell you is that the relationship between localization and fatigue work for all of the materials. So it's kind of a universal relationship.
All right.
As long as you deform slip, of course, as long as you don't have a very large defect and etc. Of course. However, the effect of the lattice rotation is still something we are investigating. We actually did test only on this material. All the other material are investigating. All of this here, they are fully recrystallized with a very nice microstructure. This one was the first one where we investigated a more advanced microstructure, and also we did this on this Rone 65. Where you can see also you have a lot of lattice rotation and etc. So yeah, the idea was can we really trigger mechanisms that prevent the localization of the plasticity, and that's something I developed. That's the main idea here. I'm trying to develop that to say you basically can engineering a material by only investigating the localization of the plasticity by slip. And so if you can prevent the slip to localize quite a lot, if you can homogenize, then you can improve the fatigue property. It worked very well for fatigue property, and now I'm trying to do that for ductility too. It should be related also to ductility.
Okay, that makes sense. Thanks a lot.
Thank you. So any other questions? I actually have several questions to ask, so probably I'll start with mine first. So thanks, JC. So what you're investigating here from the HR, EBSD and the DIC data, they are more or less 2D, right? So
yes.
So what you thinking that it will be the same when you go to the 3D bulk crack nucleation?
Yeah, it's a good question. Also, the mechanisms, they are not exactly the same, but what we extract here is really the signature of the localization. So at the surface, we basically use the extrusion, but the location is probably very similar inside the material. But indeed, the initiation may not be similar inside the material. It's not exactly the same mechanism. But the plasticity is very similar what you observe at the surface compared to what you observe inside the materials. And in order to let's see, I think I have one slide. Yeah, we use different techniques also in 3 dimension in order to capture that. Maybe one of them, I will just display this one. We use, for instance, we try to reconstruct the microstructure in 3 dimension in order to use calculation to capture the plasticity and etc. Of course, it's very difficult to observe the plasticity inside the material, the slip localization. So what we do in 3D, we can either capture by UBSD the lattice rotation. There, it's also a signature. of your plasticity. Or we also use advanced measurements where we use, for instance, topotomography is something that has been developed in France, for instance, by Henri Proudhon. And he can capture slip events inside the bulk. So you can see here it's a grain inside the bulk, and in some of the view you can capture the slip event.
I see.
But one of the issue is that it's not quantitative. So you can see the slip event, but you cannot quantify. And now they are trying to do this in a quantitative manner. But so we are going in this direction for sure.
Yeah, the quantification of these slip band would be very interesting. I would say.
Yeah, exactly.
Yeah. And another question is that so when you do the quantification, you don't have stress hold or maybe strain hold in your fatigue test, right? So, so if that's kind of like a holding is happening in the in-service conditions of the material, would that be a kind of like a problem?
Yeah, no, it's a very, very good question. So let's say I don't have the result here. I do, actually I do. Let's see. It's a very good question. Let's see. Yes, so you have this relation between fatigue strength and sleep localization. All the tests I done is basically you load and you unload, and then you do the measurement, right? And then you do the compressive part. So no hold here, and it's just a ratio of 0 or -1. And we did the exact same thing for titanium, where in this case we wanted to evaluate the dwell effect. So you maintain the load, for instance, and you have a debit in fatigue, right? In fatigue life. You don't have the same fatigue strength if you maintain the load or not. And we wanted to see if we can also capture this with the first cycle. So what we did a first cycle where we just loaded and unloaded. We measured the extrusion, or we did high resolution DIC, we quantify all the slip events. And we did the same, and here I just want to show you a small map of this. So we were not exactly able to maintain the load because our stage is not that good. So we kind of maintain the displacement here. So we have both a relaxation and both a creep. But however, what you can see is that you have an increase of macroscopic strain. And in the same time, you can capture, you have slip band, the intensity of the slip band during this load, displacement load, increase. And so you can capture that with a high resolution DIC. And so you have a real-time acquisition of your evolution of the extrusion or of the intensity of the slip during hold. And if you take the highest amplitude at the end, it fits well with the debits in fatigue. So that's worked very well also to predict the effect of dwell on the fatigue life.
I see. So you are using the last step of that holding and then to inform the dwell debit.
Yes.
Ah, interesting.
And here in this image or in this measurement, so we also can capture the dynamic. We can capture the evolution. We basically acquiring image super fast. Of course, we are limited in a small region in this case. And we acquire SEM image super fast, and we can correlate this image. And during the loading, we can capture the evolution of the slip.
Right. Yeah, that's very interesting. But I think different material would be having different maybe strain rate sensitivities, and then the creep and the stress relaxation behavior would be a bit slightly different, varying with stitch up.
Yeah, totally. We tested this on titanium 7 aluminum. And so it will be interesting to do that on 6.4 and other titanium, of course.
I see. Cool. Yeah. Any other questions from the chat? Let me see. Haven't got one yet. Thank you very much, JC, for giving us very interesting and informative talk. And you're welcome to probably discuss with our people later in our group. Oh, by the way, yeah, David, go ahead.
No, I was just going to say thank you to JC for coming.
It's a pleasure to present. So
you're welcome. Yeah. I enjoyed your talk very much.
Okay, thank you.
All right, thank you everyone for joining as well.
All right, bye.
Thank you.
Bye.
Bye.
Bye.